Okay, now let's talk a little bit about the X-ray diffractometry experiment and along with that, the conditions to run this experiment. So like we mentioned from the experimental setup, diffractometers collect our diffraction intensity as a function of 2 theta, which you can see here in figure 2.18. So we're getting it in terms of 2 theta, that's typically in degrees, and then we're getting intensity. So here it's plotting relative intensity because the total number of X-rays doesn't really matter for our experiment. It's dependent on a lot of factors. And so really we only care about the relative intensities. So that's why a lot of times you'll just see relative instead of the sort of absolute counts of X-rays. So that's another thing to keep in mind. But the main thing here that causes a lot of confusion is the fact that this experiment is in terms of 2 theta. So if you're going back to Bragg's law, that expression is in terms of theta. So you want to make sure that you keep those two straight. Okay, so this is typical data that we will see in a diffraction experiment. So the peaks here refer to those cases where we have a lot of intensity and we have a lot of X-ray intensity when the X-rays are in phase and therefore constructively interfere, and that happens at those specific Bragg conditions. It satisfies Bragg's law. And so typically we have a series of peaks against a background, so basically where the X-rays are destructively interfering. And so these peaks really tell us about the diffraction event that's occurring. And so what we need to know is for each peak, so you can see that this one has already got a label of 111, so it corresponds to a 111 plane, and then it also corresponds to a particular phase. So what we need to know to get some of this information on our own is we need to know where the peak is located, so the 2 theta value, so the peak center, and we also want to know the peak intensity. And so that's, again, always the relative intensity. So we typically call this one, which is the highest peak, we call that the 100% peak. And everything is referenced off of that peak. Okay, so to get this information, we need to look at the scan conditions for something like this. So I'm going to switch over to the paper and we'll talk about the scan conditions. All right, so now let's talk about the scan conditions we need to obtain X-ray diffraction data like we just saw in the slides. So the first thing I want to talk about is the choice of range of 2 theta. So, what we choose here for the range in which we scan our detector. So the book, our course textbook, says it gives you an ideal range of 5 to 65 degrees. And this is for most unknown materials. So the idea here is that if you don't know what your material is, you need to scan a relatively wide range of 2 thetas so that you can get as much information as possible. What we usually do in the lab is I actually usually try to kind of max out the range. And so I'll usually either go from 5 or 10 degrees up to 100 degrees. So again, it's not always necessary. You get a lot of information up to 65, but this, if you have the resources, you might as well scan a very wide range. So the low end near 5 and the high end near 100 will give you sort of different information if you're looking at different classes of materials. So polymers, for example, tend to have a lot more information on the low end, and then other materials tend to have more information on the other. So the choice there is also going to depend on what type of material you have. But again, if it's unknown, you typically want to go for a very wide range of 2 thetas. All right, so after you've kind of selected what range you want to look at, then we'll talk about choice of X-ray radiation. So if you're using a piece of equipment in the lab, a lot of times you don't actually have a lot of choice here. So it's whatever the machine is running at. And so the common one is copper K alpha. This is what our instrument in the MSE program uses, and it's the most common, is to use copper K alpha. So basically the X-ray tube has a copper target, and then we filter out the K beta like we talked about before. So a lot of times you don't have choice. But if you do, then let's kind of talk about what you would go for. And so the choice of X-ray radiation is going to affect the wavelengths. The choice of radiation is going to obviously choose the wavelength, and that kind of tells you what relative d-spacings from Bragg's law that you're going to be able to get. And so let me switch it over to the slides, and I'll show you a table with some different types of radiation. Okay, so this is table 2.4, and it shows a number of different common radiation types that are used in the X-ray diffraction community. So chromium, cobalt, copper, and molybdenum, all of those, the K alpha, because that's the most intense, because it's the most probable transition. It gives you the wavelength in nanometers, although I will say that angstroms is a lot more common, so you might see that. And the thing about each of these radiations is they're going to give you a different range of detectable d-spacings or interplanar spacings. So chromium goes up and has the highest maximum d-spacing, but doesn't go down as far. Cobalt is a little bit lower, but then goes down lower on the minimum. Copper is kind of in the middle. As you can see, it doesn't go up as high, but the minimum d-spacing is a lot lower. And then molybdenum has the lowest maximum d-spacing, so it can't detect anything above 2, but it also has the lowest. So if you're trying to get the lowest possible d-spacings, then you want to go to something like molybdenum. However, if you need the maximum possible d-spacing, so if you're looking at certain materials, a lot of almost man-made materials as well have a very large d-spacing, and so you would want to look at something like chromium. Sorry about that. And so that's why oftentimes if you have the choice, then you want to look at what types of d-spacings are you trying to measure, and that's going to kind of determine what wavelength you want to use. So the higher the wavelength, the higher the d-spacing we can capture. The lower the wavelength, the lower the minimum d-spacing that we can capture. So that's the idea in the relationship between wavelength and the d-spacing. Okay, so at this point we've looked at the 2 theta range that we want to use, and we've looked at the incident X-ray radiation source that we want to use. So now let's look at another important step that can be changed very easily, and that is the step size and width. So typically scanning, when we scan the detector and the sample in terms of theta, we don't do that continuously. So typically it's not run continuously. Instead, what we do is what's called step scan mode. So what we do is we hold the goniometer, which controls the angle. We hold it at a given position for an amount of time, so that each step is X amount of time. And then we scan, so we basically move the goniometer to the next degree that we want to look at, and so that kind of constitutes the step size. So basically, instead of, if you think about the sample here and the incident beam and the diffracted beam, so instead of scanning these angles continuously, what we do is step one increment, allow that to collect intensity data, and then step to the next after a given time, and then step to the next, and step to the next. So that's why we get the step scan mode out of that. So choosing a step width, step size, is a trade-off between accuracy in peak location and peak intensity. Right? So if I scan, if the scan size is very small, right, then I tend to get a lot of data points. But there's not much intensity at each of those data points unless I also increase the amount of time. So it's kind of a trade-off. And so if we have too narrow of steps, this can actually lead to peak shifts. And then too large of steps may suppress peak intensity. So we need to kind of be on the lookout for this. So this is, again, a trade-off. We have to kind of have it just right. But there is a guideline for this, so we don't just have to kind of guess. So the rule of thumb, so a good rule of thumb for this selection is that we want to have at least 10 data points above the full width at half maximum, or shorten that to full width half maximum. And sometimes it's also called an equations B. So we can, so I haven't brought this term up, so let me sort of sketch you what I'm talking about here. So let's say I'm just looking at one peak and I have 2 theta and the x-axis and then intensity on the y-axis like we normally do, right? So, and I have a peak, and that peak looks something like this. I drew a little badly, but more or less that's what we have. So this is the intensity is capital I and then max. So this is a max intensity. So halfway down, this is the max intensity, 1/2 of that, right? So this is basically the half maximum. So that's what we're talking about. And then we're looking at the full width. So we basically want to look at the peak width at half the maximum. So basically this is what the B, or full width half maximum, is referring to. So it's basically a standard way of measuring how wide the peak is. So we're doing it at half the maximum intensity, so the peak intensity that we have here. So for this rule of thumb for our step size and width, we want to have at least 10 data points. So we want to make sure that we have 10 data points, right, above this full width half max. So we want to make sure we have an appropriate amount of data points in that case. So that's what we're talking about in terms of this rule of thumb. So if we want to think about this in terms, so you don't really know this until after you've run the experiment. And so for a typical peak, with a full width half max of between 0.1 and 0.3 degrees, that's a pretty common full width half max, then a step size of 0.02 degrees in 2 theta is reasonable. So this kind of step size is pretty common to have a good measure of the peak.